Hi everybody. Thanks again for playing along with all this stuff. You guys are really doing well. I'm very impressed how everybody is kind of getting it done through the e-learning COVID freakout. Um, I know that this one's tricky, so I wanted to help you out with a little bit. So just to kind of walk it through a little bit. We've got 24 volts here. Notice how there's multiple batteries there stacking up to give us 24 volts of push. And then you got three different resistors. This must be a light bulb. There's another one. There's another one. Or who knows? Maybe it's a toaster. Maybe there it's a foot massager and possibly an aquarium um, filter. I don't know. All right, so we do the thing where the voltage is highest. It's going to be 24 volts. So it's 24 volts of push all the way through where it's red. Then we go to where it's lowest. It's going to be 0 over here. So we're going to cover that in blue the whole way. Then, of course, they each hit a resistor, so they got to go down or up, as it were. So from red, it goes to orange. And from blue, it would upstream from that would be green. All right, so what we have here is the potential starts at 24 volts over here and ends at 0 volts, which means it has to lose some of that push at each of these resistors. They might not all be the same, so we can't just assume it's going to lose 8 volts there, and then this would be 16, and then it'll lose 8 here, and this would be 8, and then it'll lose the last 8, and this would be 0. Think about what I mean by that again. It starts out at 24 on this side, needs to get to 0, and has to lose it in 3 different places. If they're all exactly the same, it'd lose 8 volts here, another 8 there, and another 8 there. But that's not the deal here. The deal here is you can see that they all have 2 amps flowing through them, and that makes sense because it's only one continuous loop. So however fast an electron is moving here, it has to move the same speed here. Remember, if you push one in, one's got to come out. So all of this has to flow at the exact same speed, and that we see. It says 2 amps through the first one, 2 amps through the second, and 2 amps through the third. Remember, amps measures current, and current describes how fast the current is flowing, how fast the charge is flowing. But the big difference here is notice these resistors are different. This first one is 3 ohms, the second one is 4 ohms, the third one is 5 ohms. So which one of those is harder to get through? The 3 ohm resistor, the 4 ohm resistor, or the 5 ohm resistor? That's right, good job. The 5 ohm resistor is harder to get through than the 4 or the 3. So that means of the 24 volts that we're starting with, most of it is going to be used getting through here. This is only 3 ohms. That's not much resistance. That means it's easy to push current through there, so we're not going to use up much of the 24 volts of push that we have. Now, how do you figure this out? We'll go back to Ohm's law. So let's just take a look if I can. If I can hold up. Okay, so here I am trying to show you. This is my own drawing of that. It should be similar to what we just saw. We've got 24 volts. We've got to lose all those volts as we go through here. All right, the first one is 3 ohms. So remember this guy. V equals, sorry, erase. Start over, sorry. V equals IR. So here you've got amps, that's I. Here's your resistance, R. Hey, wait a minute. If I multiply I times R, I should get V. So if I multiply 2 amps times 3 ohms, that's 6. 6 watts. Turns out it's 6 volts, kids. So let's figure that all the way around. If I take this one, V equals IR, V equals 2 amps times 4 ohms. This one's 8 volts. We'll talk about what that means in a second. And down here, that's 10 volts, 2 times 5. So what do these numbers mean? 6 volts, that 8 volts, and that 10 volts. Well, what that means, my friends, is that we start out at 24 volts. And all the way that it's red, it's still pushing with 24 volts, which is worth a push, all the way through until it gets to there. And because this is a relatively easy resistor to get through, we only use up 6 volts of push. So on the other side, what's the voltage? 18 volts, 24 minus 6. It loses those 6 volts. 18 volts all the way around, volts. Now here, it's a little bit harder to get through because that was 3 ohms of resistance. This is 4 ohms of resistance. So how many volts does it take to get through there? 8 volts. So we started at 18. Then how many volts are left over here? You guessed it, Chester. 10 volts. 18 minus 10. 10 volts. So it's 10 all the way through here. Now it's got to get down from 10 to this last one. What's the voltage at the blue part always? It's 0. You remember that? That's 0. So ultimately we're trying to get from 24 volts to 0. Lose all that push. So here we've got 10 volts left, and check it out. 2 amps times the 5 ohms of that resistor equals 10 volts. That's all we have left. So we start with 24, lose 6 volts of push through this 3 ohm resistor. Then we only have 18. Then we lose 8 volts of push through this 4 ohm resistor, and there's only 10 volts left. And then we lose the last 10 volts, this 5 ohm resistor, and we get to 0. All right, use that thinking as you go through these problems, and I think you're going to be okay.